In October 2013, one of the most important government software systems in US history went live. Within hours it was failing. Users saw frozen screens, account creation loops, identity verification errors, endless loading spinners. This was Healthcare.gov, the central online marketplace for the Affordable Care Act. It wasn't just a product launch, it was a political event, a legal milestone, a national headline. And when it failed, it became one of the most studied software collapses of the modern era. But here's the important part. Healthcare.gov did not fail because developers didn't know how to code. It failed because architecture collided with politics, procurement, and organizational structure. Today we're going to break down what Healthcare.gov was designed to do, why its architecture was inherently high risk, how organizational structure shaped technical outcomes, what happened during launch, how it was rescued, and what this means for you as a software engineer. This is not a story about bugs, it's a story about systems. 1. The mission, more than a website. Healthcare.gov was not just a website, it was the digital execution layer of the Affordable Care Act. It had to create secure user accounts, verify identity and citizenship, check income with the IRS, determine Medicaid eligibility, calculate federal subsidies, enroll users with private insurers. Each enrollment required real-time coordination across federal agencies, state systems, and third-party vendors, most of which the Healthcare.gov team did not control. This wasn't a simple application. It was a national integration engine. 2. The scope problem, national rollout, day 1. One of the most consequential decisions was not technical. It was strategic. Healthcare.gov did not launch regionally. It did not launch as a beta. It did not roll out gradually. It launched nationwide on day 1. This meant millions of potential users. National media attention, zero margin for staged failure. In modern software as a service, we mitigate risk through feature flags, gradual rollouts, canary deployments, beta programs. Healthcare.gov launched as if it were version 1.0 of a national operating system. There was no soft launch. There was no, we'll invite 10,000 users first. The political and legal environment required it to be fully operational on October 1st, 2013. From a systems engineering perspective, that dramatically increases risk, because distributed systems fail in ways that are difficult to predict. And when your first real stress test is production at national scale, you are performing a live experiment in front of the world. 3. The architecture, a centralized data hub model. The core design centered around a federal data hub. Think of this hub as an orchestration layer. Instead of every agency talking directly to every other agency, Healthcare.gov routed requests through this central integration point. Conceptually, this has advantages: standardized interfaces, centralized orchestration, controlled request flow, but centralization also creates bottlenecks, single points of failure, shared infrastructure contention. Now add synchronous dependencies. A single user enrollment could require real-time calls to the IRS, real-time calls to DHS, real-time calls to state Medicaid systems. If one system slowed down, the entire request path stalled. There was limited tolerance for degraded performance. No meaningful queue-based architecture for asynchronous completion. The design assumed that external systems would respond reliably and quickly. In real distributed environments, that assumption rarely holds under peak load. This wasn't just architectural complexity, it was architectural fragility under scale. 4. The hidden risk, synchronous eligibility chains. Let's zoom into one user flow. A user creates an account. Behind the scenes, credentials are validated. Identity is verified. Income is checked. Citizenship is confirmed. Eligibility is computed. Plan pricing is recalculated. Each step is dependent on the previous step. Each step depends on external systems. This creates a synchronous dependency chain. In distributed systems, synchronous chains amplify risk because latency accumulates across services. Timeouts propagate, retries increase load, cascading failures emerge. If identity verification takes 500 milliseconds longer than expected and that service experiences retries, you can easily trigger database contention, thread pool exhaustion, log flooding, session expiration. Under moderate load, this may not appear catastrophic. Under national launch traffic, it becomes systemic. This is one of the most important lessons from Healthcare.gov. Distributed systems are not linear in their failure behavior. They degrade exponentially. 5. The testing gap, components versus reality. From public reports, individual modules were tested. Subsystems were validated in isolation, but the entire system under realistic concurrency, not sufficiently. This is a classic failure mode. Teams test, unit logic, service level integration, API contracts, but they do not simulate millions of concurrent users, network latency variability, partial external system failure, cascading timeout amplification, log throughput under stress. In large systems, emergent behavior only appears under integrated load, database locking behavior under concurrency, thread pool starvation, queue back pressure, unexpected retry storms. If you don't test full stack under realistic traffic patterns, your first true test is production. Healthcare.gov's first full-scale integration test was the launch itself. That's not an engineering strategy, that's a gamble. 6. Organizational architecture, fragmented ownership. Now we move to the most underestimated factor. Healthcare.gov was not built by a single cohesive engineering organization. The primary contractor was CGI Federal. But multiple vendors handled different components. Multiple federal agencies had oversight roles. Political leadership imposed milestones. There was no unified engineering authority with end-to-end control, and this matters profoundly, because reliability requires clear ownership of integration boundaries, clear responsibility for performance budgets, clear authority to delay launch if necessary, clear accountability for system-wide behavior. Instead, responsibility was distributed. Subsystem teams optimized locally, but no one owned global behavior under stress. This is Conway's law in action. System structure mirrors communication structure. Fragmented oversight to fragmented integration discipline. When things began failing at launch, the question wasn't just what broke. It was who owns this failure? In high-performing engineering organizations, ownership is explicit. In politically complex procurement environments, ownership can become diffuse, and diffuse ownership produces fragile systems. 7. Launch day, when theory meets reality. On October 1st, 2013, Healthcare.gov went live. Within hours, it was clear that something was wrong. Users reported being unable to create accounts, endless identity verification loops, sessions timing out, generic error messages, pages freezing after submission. From the outside, it looked like the website crashed. From the inside, it was more complicated. The system wasn't failing in one place. It was failing everywhere at once. Account creation triggered a cascade of back-end calls. Under load, those calls began to queue, stall, retry, and amplify one another. Databases experienced contention. Logging systems became overloaded. Monitoring tools struggled to provide clear visibility. One of the most damaging early design choices was the requirement that users create accounts before browsing plans. That meant even curious users, not just serious buyers, triggered the most complex backend flows. This dramatically increased system load. In distributed systems, small inefficiencies multiply under concurrency, and when you combine high traffic, synchronous dependencies, limited back pressure controls, poor observability, you get nonlinear failure. The system didn't degrade gracefully, it collapsed chaotically. 8. The visibility crisis, flying blind under pressure. One of the most under-discussed aspects of the failure was observability. When a system fails under load, you need answers fast. Where is the bottleneck? Is this a database issue, a network saturation problem, a thread pool exhaustion issue, an external dependency timeout? Reports from the period indicate that monitoring and telemetry were insufficiently integrated across vendors. Different teams had different dashboards. Metrics weren't unified. End-to-end tracing was limited. In modern cloud-native environments, we take for granted distributed tracing, real-time metrics aggregation, centralized log pipelines, automated alerting thresholds. In 2013, especially across fragmented government contractors, this level of integrated observability was not fully mature. Without visibility, debugging becomes reactive. Instead of, here is the precise choke point, you get, something is wrong somewhere. And during a nationally televised launch, that ambiguity is dangerous, because engineering needs clarity, politics demands speed, and speed without clarity increases risk. 9. The political fallout, engineering under national scrutiny. Healthcare.gov wasn't just an IT project, it was a central pillar of the Affordable Care Act. When it failed, it became a national news story, a partisan debate, a congressional investigation topic. This transformed a technical stabilization problem into a political crisis. Engineers weren't just fixing load balancing, they were operating inside media scrutiny, legislative oversight, executive pressure. This environment shapes decision-making. In a private company, a failed launch might result in an internal postmortem, a quiet rollback, a delayed re-release. In this case, public trust was at stake, policy legitimacy was questioned, political capital was being spent, the pressure to stabilize was immense, and pressure can distort engineering priorities. Instead of long-term architectural rethinking, the immediate goal became make it work, now. That urgency led to the next phase. 10. The tech surge, stabilization, not reinvention. After the failed launch of Healthcare.gov, a recovery team, including engineers from Google, Amazon, and Microsoft, focused on stabilization rather than redesign. They centralized technical leadership, clarified ownership, improved monitoring, optimized database performance, increased infrastructure capacity, and narrowed scope to the most critical flows, account creation and enrollment. The system wasn't rebuilt, it was simplified, prioritized, and made observable. By December 2013, it was functioning at scale. 11. The core lessons. Healthcare.gov shows that large systems fail at integration points, not just in code. Synchronous dependency chains amplify risk under load. Fragmented ownership weakens reliability. Immovable deadlines shape architecture whether engineers like it or not, and without strong observability, recovery becomes guesswork. The deeper lesson is simple. Software systems are socio-technical systems. Architecture must account for both technical complexity and organizational reality. 12. The broader perspective. Architecture always meets politics. It's tempting to view Healthcare.gov as a uniquely governmental failure, but its dynamics exist everywhere. Replace federal agencies with internal departments, contractors with microservice teams, congressional deadlines with investor commitments, public hearings with enterprise client escalations. The structure remains. Large-scale software projects operate inside incentive systems, communication hierarchies, governance frameworks, budget constraints. Architecture does not float above these forces. It is shaped by them. When politics and architecture collide, politics often dictates the launch date. If architecture is not mature enough to survive that collision, failure becomes visible. Healthcare.gov ultimately stabilized and enrolled millions of users. But its launch remains a defining example of this principle. Software systems are socio-technical systems. They are built not just from code, but from communication structures, incentives, and institutional pressures. If you want to think like a software engineer, not just a programmer, you must understand both layers, the technical architecture and the political architecture surrounding it, because in the real world, they are inseparable. If you found this case study useful, this is exactly what this channel is about. We don't just talk about code. We explore how real-world software systems are built, why they fail, and how good engineering teams think differently. If you want to understand not just syntax, but architecture, system design, and how software operates at scale, subscribe to The Shape of Software. And if you want a structured next step after this video, I've linked a beginner-friendly software engineering learning path on Coursera in the description. It's a guided way to build the foundations, programming, workflows, and how real projects run, without having to guess what to learn next. If this helped clarify something for you, leave a like. It really helps the channel. And tell me in the comments, which real-world software system should we analyze next? Thanks for watching. I'll see you in the next one.